You've already seen, many times in your life, the light of a star that has passed through a planet's atmosphere. You've already watched a sunset. We are able to measure the variation in temperature depending on the altitude of a planet located a few hundred light years away from us, one we've never seen. One of the great lessons from the last 30 years of exoplanetary system discoveries is diversity. Many people are actually trying to find another Earth. It's kind of the holy grail for a number of people who are searching for exoplanets.
Hello, Alain Le Cavalier. Hello, we're very happy to have you on the show. So, for those who don't know you, can you introduce yourself? Yes?
So my name is Alain Le Cavalier des Étangs. I am an astrophysicist at the CNRS. I also teach astrophysics at the École Polytechnique. And I have been working in astrophysics for nearly 30 years at the Paris Institute of Astrophysics, which is a CNRS laboratory. And I am fortunate to be able to work on all the questions we have about planets and comets, mainly outside the solar system.
So, actually, you work a lot on what we call exoplanets. And what is your field of study regarding these exoplanets? Do you want to track them? Are you trying to understand them?
Personally, deep down, I'm not looking for exoplanets. I study the exoplanets discovered by my colleagues, okay? So I listen to all my colleagues who are tracking these exoplanets, which we've been discovering for more than 30 years now. I was fortunate to begin my career as the first exoplanets were discovered. And I specialize more in studying the planets that have already been discovered, the most interesting ones that we can characterize. For example, we observe their atmospheres. And recently, I've been particularly interested in what we call exocomets, which are small icy comet bodies that orbit stars other than the Sun, but that come close to their star, which evaporate and produce gigantic tails of gas and dust, like the comets in the solar system that we see in the sky from Earth.
All right, so to set the scene a little bit, you said that exoplanets, the study of exoplanets, is something that's fairly recent. How is it that it's so recent when in fact we've been able to detect galaxies that are much farther away for quite a bit longer? Yes.
Actually, seeing exoplanets is very difficult, really. It's strange, but these objects are very close. You know, the stars around which we find exoplanets are stars in our cosmic neighborhood near the solar system, actually. They're very close, only a few hundred or thousand light years away at most. It's the neighborhood in our galaxy. But it's hard to see them, to detect them, because they orbit close to their star. They don't emit any light. They only reflect it. The planets we see, like Jupiter and Saturn, reflect the light of their star. If you look up at the night sky, the very bright object you see is Jupiter. In fact, it's not Jupiter's own light that you see, it's the sunlight reflected by Jupiter. So, planets don't emit light, they only reflect the light of their star, and they are very close to their star since they orbit around it. So, when we observe stars in the sky, we're dazzled by the light of the star, and the light from the planet is almost undetectable or very, very, very difficult to detect. So, to discover these objects, we had to wait until the mid-90s when we had techniques that were advanced enough to use so-called indirect techniques. That means we don't detect the light reflected by the planet. We don't see the planet in an image like, oh, there's a bright spot, that's the planet. Some of them we do that, but a bit later. We detect the influence of this planet on the light we receive from the star. So we study the light from the star. And if that starlight carries information about the presence of something around it that influences it, we indirectly deduce the presence of a planet. And for that, there are two different techniques that have produced very, very effective results. The first one that has been used historically is the radial velocity method. Well, what that means is that we measure the speed of the star, not the speed of the planet, the speed of the star, because the planet orbits around the star. In practice, it's not the planet that orbits around the star. In physics, both of them orbit around the center of gravity of the two. So, in other words, the planet orbits around the star because of the gravitational pull of the star on the planet. But conversely, action and reaction, there's the gravity of the planet acting on the star. The planet makes the star move slightly, much less than the planet does because the planet is much less massive, but it still causes some movement. And if we measure this movement, by measuring the speed at which the star moves, we can detect the presence of an object that's making the star move, so the presence of a planet. This is what's called the radial velocity method. In fact, we measure the speed using the Doppler effect. It's exactly the same way, the same method that the police use when they catch you with a speed camera on the highway to measure the speed of your car.
Which means that actually the expression, the Earth revolves around the sun, isn't scientifically accurate.
It's a good approximation, but in practice, the Earth revolves around the center of gravity of the solar system, which is made up of the Sun, but also the other planets like Jupiter, which is the most massive in the solar system, Saturn, and so on. And if we look at the movement of the Sun in the galaxy, well, this movement, it moves like this, it turns a little. Because the planets Jupiter, Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury make the Sun move at the same time.
I'm extrapolating a little bit. Let's imagine a scenario where the planet would be as heavy or even heavier than the sun. Could there be a sun that actually orbits around a giant planet then?
In physics, if two objects have the same mass, like in binary star systems, which we know exist, both orbit the center of gravity, moving around each other. That's exactly what we observe in binary systems. But if we had an object with the same mass as a star, the mass of the Sun in that case, this object would be massive enough to start thermonuclear fusion reactions at its core. It would produce energy, it would be luminous, it would be a star. So a planet is an object that is not massive enough for thermonuclear fusion reactions to start inside it and for it to shine by itself.
There, you worked on something that I find even crazier than just detecting planets. It's about understanding a little bit how they work, the composition of their atmosphere, the weather there. How can we go that far into the details and understanding of these exoplanets?
Well, that gives me the chance to explain the second method because I haven't explained it yet. Yes, I explained. There are two methods, that have produced extraordinary results in discovering many planets. Well, actually, now we're getting to the second most prolific method. There are still 3 or 4 other methods, but they're more difficult to implement. The second method that has led to a huge number of exoplanet detections, several thousand now, is what we call the transit method. So this time we're not measuring the influence of the planet's gravity on the star, but rather we're measuring the effect of the planet passing in front of the star and blocking some of the star's light. So it's still an influence of the planet on the light we receive from the star, but it's not a change in the star's velocity, it's a change in the star's brightness. So we measure the brightness of the stars, and when the planet passes in front, it blocks just a little bit, not much. Even if we take a planet like Jupiter, which is the largest planet in the solar system, if it passes in front of the Sun, seen from very far away, Jupiter is about 1/10 the size in radius of the Sun. So that means in terms of surface area, it's squared, so that's 1/100th. So when Jupiter passes in front of the Sun's brightness decreases by 1/100th. It's the biggest planet in the solar system. When it's Earth, Earth is another factor of 10 smaller. Roughly, Earth is a little less than 1/100th the size of Jupiter in radius, not in volume, but in radius in diameter. And so 1/100th will give you 1/10,000th. So when a planet the size of Earth passes in front of its star, the brightness of the star decreases by about 1/10,000th. It's not much, but we can detect it thanks to space observatories. In fact, we had the Corot missions, which were launched by France and Europe. There's the Kepler mission, which was launched by NASA. And currently, we have the Cheops mission, a space observatory from the European Space Agency, and then the TESS mission from NASA. So there are plenty of, we've launched space missions to measure the brightness of stars and see if periodically the star becomes less bright. And when we detect that it's less bright, let's say every month, once a month, we say there's a planet orbiting the star that passes in front of it and decreases its brightness. So 1% if it's the size of Jupiter, 1/10,000th if it's the size of Earth, and this happens periodically. So we measure instantly, well, instantly. Once we've made these observations, we immediately have the measurement of the orbital period. So we can deduce how far this star, this planet, is from its star, and we have the measurement of the size of the planet. We know if it's a giant planet that causes about a 1% drop in brightness, or a terrestrial type planet that causes a drop in brightness of about 1/10,000th. So then your question was, how do we study these planets, since in the end we don't actually see them? As I told you, we detect them indirectly. How are we going to be able to study objects that we can't see? Well, it turns out that the light coming from the star is less bright when the planet passes in front of it because it's being blocked. But there's a part, a very small part of the star's light that passes through the planet's atmosphere. And when the star's light passes through the atmosphere, well, it leaves its signature in that light. And so we can characterize the planet's atmosphere if we detect it, and thus learn much, much more about a planet we've never actually seen.
So here we're talking about 1/10,000th, which roughly corresponds to the surface area of the planet compared to the Sun, and an even thinner surface that corresponds to the atmosphere of that 1/10,000th of a star that's located on the other side of the galaxy.
Not across the galaxy, but in our area. For stars bright enough, you can usually see them with binoculars. And so actually, you said it was 1/10,000th. That's for the atmospheres of planets the size of Earth. We're starting to do it with the James Webb Telescope, for example, but it's still very difficult. The first atmospheres we've characterized are those of giant planets. You see, it's a 1% drop in brightness, and within that 1%, well, there was possibly 1,000th, 1/10,000th. That was due to the part of the light that had passed through the planet's atmosphere and that we can characterize. So for that, we use the technique called spectroscopy. We break down the light that reaches us, and depending on which colors are missing or present, we can then determine properties like the composition and possibly the temperature. I'll give you an example. In fact, you've already seen many times in your life the light from a star that has passed through the atmosphere of a planet. Well, you've already watched a sunset. Yes, yes.
Yes.
Well, when you watch a sunset, you're observing the light from a star that has passed through an atmosphere. In this case, it's Earth's atmosphere. And when the sun is low on the horizon, it goes through a huge layer of the atmosphere, and that's why the sun looks red. The sun looks red because sunlight contains all the colors. You know, white, the white light from the sun, the white light from the spotlights shining on us here. It's a mix of all the colors of the rainbow, from blue to red, that's it. But the Earth's atmosphere has the property of absorbing more of the blue, green, violet, blue-green colors, and so on, than the orange and red colors. All right, and that's related to what's called Rayleigh scattering. And so when you see the sun low on the horizon, the only light that reaches you is the red light. That's why the sun appears red and less bright. You can almost look at it without shielding your eyes. Still, you shouldn't stare at it for long, even near the horizon. Let me take this opportunity to say, never look directly at the sun because it burns your retinas and it's irreversible. So don't stare at it, but you can clearly see that the sun near the horizon is much less bright than the sun at its zenith. And it has changed color. It's much more reddish, orangish, reddish. And so just the combination of the two makes us realize that it's not just that it changed color, it's that some colors have been removed. And we've removed the blue, so the sun appears red. Well, for exoplanets, it's the same thing. At one point, we observed giant planets passing in front of their star, and we looked at the colors of the light coming to us from the star. And then we saw the light drop a lot, for example, by 1% if the planet is the size of Jupiter, but in that 1%, the drop is a little greater in the blue. Okay? And it's a little bit more in the blue. That's the signature of the part of the blue light that was absorbed by the atmosphere, while the red passed through like a sunset. And that allows us to characterize the physical properties of the atmosphere. And for example, with this experiment I'm describing to you, it allowed us to measure the temperature of the atmosphere of exoplanets.
We can get the temperature.
Yes, because actually the principle is as follows. It's that when you measure this absorption by Rayleigh scattering that I was describing to you, actually you then have a measurement of the atmosphere's height. And the height of the atmosphere is directly related to the temperature. If you have a very hot atmosphere, it can extend to high altitude, which is what we call the scale height, which is proportional to the temperature. So there's really the height of a planet's atmosphere, how the pressure and density decrease with altitude. So this height of the atmosphere depends on the temperature. And by measuring how much Rayleigh scattering there was in the planet's atmosphere, we were able to measure the height. We make the assumption that it's what's called a hydrogen atmosphere, like the atmosphere of the planet Jupiter, because the composition also comes into play a little bit. And we do a calculation that you can really do in your final year of high school. I mean, really, it's a very, very simple calculation, and we can deduce the temperature of the atmosphere. And we can even go further. It's pretty incredible. When you think about it, since we see this absorption, and it's different at different altitudes of the atmosphere, we can even measure the temperature depending on the altitude in the atmosphere, and see that, for example, the temperature decreases or increases depending on the altitude. You know very well that on Earth it's colder at the top of Everest than at sea level, of course. Well, it's the same thing in the atmospheres of exoplanets. There are several atmospheric layers, but there's a layer where it's colder at higher altitudes than at lower altitudes. And with Rayleigh scattering, we can measure, roughly speaking, over a few hundred kilometers. But still, you see, we're able to measure the variation in temperature as a function of altitude. A few hundred kilometers above a planet that's a few hundred light years away from us, one we've never seen. We've only ever seen its shadow, yeah. And we've studied the light from its shadow to deduce all its properties.
Yeah, it's crazy. And so, to be able to observe such weak signals, you need extremely precise instruments. So what can we use then to...
That's the difficulty. And you really need extremely stable instruments because the planet takes a few hours to pass in front of the star, so you have to observe at the right moment. We don't have much time. And so you have to measure drops in brightness that are on the order of a fraction of a percent, and in very precise wavelength bands. So you need instruments with absolutely remarkable stability. And actually, the best instruments we have for that are the ones we've sent into space. Because in space, everything is stable. There are no uncontrolled temperature changes, and any that occur can be managed. Earth's atmosphere isn't there either. Because when we observe from the ground, well, we observe the light coming from the star, but it has also passed through Earth's atmosphere, so it adds signatures that make things a bit more complicated. It's possible, but it's still more complicated. So the instruments that have given the most extraordinary results are the Hubble Space Telescope and the James Webb Telescope, now which allow observations in the infrared, which therefore allow us to observe these exoplanet atmospheres, to measure physical properties, such as the temperature I mentioned, but also to detect elements and also to see phenomena like, for example, atmospheric escape, which is one of the first phenomena that was detected at the Paris Institute of Astrophysics. So atmospheric escape from planets that are losing their atmospheres. Okay, that we're right in the middle of it. We have the ability to detect it, yes. And so when it comes to atmospheric escape, maybe this is a good opportunity to tell you a nice story about a discovery. Since it was, well, now it's been a little more than 20 years ago, we had just discovered the first exoplanets. In fact, the first exoplanets, the first ones we discovered around pulsars, neutron stars, the remnants of stars, that was in 1992. And then the first one around a sun-like star was discovered by Michel Mayor and Didier Queloz in 1995 at the Haute-Provence Observatory in France. They were Swiss astronomers who used a telescope at the Haute-Provence Observatory a 1.93-meter telescope at the Haute-Provence Observatory. And so the first discovery of exoplanets around a sun-like star was in 1995. And then at that point, we realized that these techniques worked. We discovered more and more. And then at the end of the 90s and the beginning of the 2000s, we discovered the first transits, planets passing in front of their star. So there at the Paris Astrophysics Institute, in the team where I was with Alfred Vidal-Magyar, Jean-Michel Désert, Guillaume Hébrard, well, it was really a team effort. You need to understand it's not just one person working. So in the team we thought, hey, this planet passes in front of the star, maybe we'll be able to see the atmosphere. That's what I just described to you. And we submitted a proposal to use the Hubble Space Telescope to observe the planet passing in front of its star, thinking to ourselves, let's try something. It was really something no one had ever done before, you know. Just an idea, well, somewhat based on some calculations, but no one had ever done it before. And we thought it should be possible. And let's observe something we know well, which is hydrogen. It's the most abundant element in the universe. And so giant planets, if it were a giant planet like Jupiter, we can imagine that hydrogen is very abundant. That made sense. Hydrogen has another characteristic. It's a very light element. It's the lightest element in Mendeleev's periodic table, so a light element is also one that will rise very high in the atmosphere. And as we can see, if we want to observe the shadow of the atmosphere passing in front of the star, well, if it goes very high, it will be easier to detect. And it turns out that in Alfred Wiener-Magyar's team, we had very good knowledge of ultraviolet observations. And it's possible to observe hydrogen in the ultraviolet with the Hubble Space Telescope. So we thought, with all this combined, let's try observing the planet passing in front of its star with Hubble. And we made this observation. And I like to tell this story. I tell it. I often tell it when I have the opportunity to give presentations to middle school or high school students to explain to them how discoveries are made. Because sometimes it feels like discoveries happen when you just get an image and say, look, I found it, and so on. But actually, that's not how it is. It's a lot of people interacting with each other, exchanging ideas and saying, hey, we could try this. The other person responds, no, that won't work, but your idea gives me another one. Maybe this will work. You observe these exchanges. And when we received the data from the Hubble telescope, that's exactly how it was. There was one among us who we didn't understand anything and we couldn't see anything. And the data seemed completely useless to us. And so we spent a few weeks trying to get something out of it, and then it just wasn't working. So we put them away in a drawer saying, well, we gave it a shot, but it didn't work. It's not a big deal. It happens in life. You have to try. That's it. Then, a few months later, we said, still, it's a shame to let this amazing observational data on a planet passing in front of its star go to waste. Maybe we should try again. So we try again. We only uncover a few problems that were in the data that we managed to fix. It works better, but it's still not conclusive. And then we give up. Then a few months go by. Then I remember Alfred and I saying it was still a shame not to pursue it. So we went back to it. With the help of Jean-Michel Désert, who did a very detailed analysis of something that was really bothering us. It was the temperature rise of the detector, which wasn't known at the time. Now it's something we know very well. But at the time, it wasn't well characterized for the Hubble telescope.
What does the temperature rise of the detector actually involve?
It turns out that the telescope, well, it's in space, but it orbits around the Earth. So there are times when it's exposed to the sun, and there are times when it's in the Earth's shadow. So there are temperature changes in the telescope, and the detector, when it heats up, there's a bit more thermal emission. So there's a background image that increases and really interfered with the interpretation. We wanted to observe a change. We aimed to characterize the difference when the planet is in front of the star versus when it's not. We distinguished between the two. The detector's temperature rose, so we interpreted it that way. But background noise increased and became very disruptive. Eventually, we figured it out. And so you see, that actually took months, because at some point we were tinkering with it and it just wasn't working. And then one day, But that's it, actually. That's how you have to approach the problem. Here's the problem. Here's how to deal with it. So once you have the idea, it's always the same, really. Once you know what needs to be done, it's just a matter of technique. Almost everyone knows how to do it. On the other hand, what's difficult is knowing what needs to be done. Eventually, we realized we knew what to do and that it worked. And then we got a nice light curve. Finally, we can see the difference of this line, this hydrogen H alpha line, between the moment when the planet was in front of the star and the moment when the planet was not in front of the star. And we see a big difference. And so there, again, same thing, we don't understand anything. The difference we observed was completely unexpected. And what we see is that the drop in the star's brightness when the planet is in front, in the hydrogen line, it's not, you see earlier I told you 1/10,000th, 100th, etc. It was 15%, okay?
Okay.
Whereas the planet only blocks 1% of the star. Here, 15%, there's something wrong. What's going on? And actually, afterwards we thought about it. We said to ourselves, let's try to understand. First, we have to make sure it was a good detection. And that's difficult because we think maybe there's something we did wrong in our data analysis. Once we were convinced of that, we said to ourselves, no, it must be true. Then we had another measurement, which was the speed of this gas. That's the Doppler effect I was telling you about earlier. For the measurement of, well, we can also measure the speed of the gas. And this gas was moving at 130 kilometers per second. An enormous speed. And then we said, that's it, we understood. Well, it took us some time, but at some point we understood. It was gas escaping from the planet's atmosphere, and that's why it's a huge cloud of gas that's much bigger than the planet, and it moves very fast, because it's gas escaping from the planet.
All right. So when we talk about speed, it's speed relative to the planet, right?
Exactly. Relative to the planet, it was moving at 130 kilometers per second. And that's how, in fact, it wasn't the first, it was the second, because other American colleagues simultaneously, in fact, had similar ideas and observed sodium. But almost simultaneously, those were the first observations of exoplanet atmospheres. And then the observation and discovery of a phenomenon we hadn't imagined, atmospheric escape from the planet's atmosphere. And why does this atmospheric escape, this gas leaving the planet, happen? It's simply because this planet is very close to the star. This planet isn't like Jupiter. It orbits its star in just 3.5 days. It takes 3 days to complete an orbit, while Earth takes a year. Earth takes a year to go around. Here, it's a planet that's very close, that's very hot. Really, the temperature is very high, and this high temperature allows the escape of the lightest gas only, well, essentially the lightest gas, hydrogen, which has been observed and thus discovered. Atmospheric escape. Planets very close to their star, which lose a small part of their atmosphere.
But then what causes the atmosphere to escape is not directly the solar wind, it's the temperature of the star. So
Yes, well,
the temperature of the planet then.
the temperature of the planet, the atmosphere of the planet. Actually, it's an atmosphere that is heated by the ultraviolet radiation from the star. And it's the outer part of the atmosphere that's very hot, much hotter than the lower part. And this outer part, well, that's exactly where the light elements are, and they can escape. And since it's at such a high altitude, gravity is a bit weaker. So there are both these phenomena, this balance between gravity that keeps the atmosphere on Earth. The atmosphere we breathe here is held by gravity. The attraction that keeps me in this chair also keeps the atmosphere here. All right. And the Earth's atmosphere, even today, the atmosphere escapes a little bit from the Earth, but very little because it's not very hot. And there's the Earth's gravity. Here, it's very close, it's very hot. Heated especially in the upper part of the atmosphere, and it escapes and can lose enough material to be detected even though we still haven't seen the planet itself.
Are there any planets that stood out to you where there were discoveries that were perhaps surprising?
Well, yes, that planet orbiting the star HD 209 458b So you see, it's a bit of a complicated name. It's the first one for which a transit was detected, for which atmospheres were detected, and so on. So yes, it's really a planet that made a big impression. There was just one discovered a little later, which is HD 189 733b. Yeah, those are strange names, I'm sorry. Then there's another one of the same type for which we've been able to do a lot of observations of the atmosphere, atmospheric escape, and so on. And now there's a planet that interests us a lot as well. It's Beta Pictoris b. So it's a planet that orbits a star called Beta Pictoris. Instead of just saying it's an interesting planet, this one fascinates me because we actually photographed it. Earlier I mentioned we usually find them indirectly. It turns out that this planet, Beta Pictoris b, Anne-Marie Lagrange's team from the Paris Observatory was able to take a picture of it. We have very few images of the light emitted by the planet. And here for this planet we do have some. Thanks to the techniques, so here these are ground-based instruments, but with techniques of adaptive optics that allow for extremely high performance observations and to detect planets like this one, Beta Pictoris b. But actually I'd rather talk to you about Beta Pictoris, because Beta Pictoris is the name of the star. And so the planet that orbits around it is called Beta Pictoris b, and even Anne-Marie Lagrange discovered another planet, Beta Pictoris c. So today we know that there are at least two planets in this system. But it's a complete planetary system. Because there's not only a star at the center, two planets, at least two giant planets orbiting around. There are also plenty of small bodies, asteroids, comets, even tiny dust particles and gas. It's a complete planetary system. And here it's really, well, it's absolutely wonderful that we're lucky to have a complete young planetary system so close to the solar system. I mean, it's about 60 light years away, so really close to us, and it's seen edge on. It's a planetary system, so everything lies in the same plane. And it turns out that the Earth, the solar system, is in the orbital plane of all these objects that orbit around Beta Pictoris. And so we're lucky to be able to observe these objects passing in front of the star, the transits I was just describing. And so we can see the planet moving like this, well, orbiting, we capture an image of it. But we can also see objects passing in front of the star. And we see, among other things, what we call exocomets, comets, small bodies that evaporate, that approach the star, that evaporate and create huge comet tails. Just as we observe comets in the solar system and see their tails, and when they pass in front, well, we see the signature in the light of the star. Same thing, always the same technique. And then we make lots and lots and lots and lots of observations of these objects.
So just a quick side note before we go any further. We tend to confuse comets, asteroids, and meteorites. Could we do a quick recap of the different categories?
The different categories, yes, the small bodies. Because actually in planetary systems, there are the planets, Jupiter, Saturn, the big giant planets, gas giants, Jupiter, Saturn, the planets we sometimes call ice giants, because they contain a lot more volatiles, water, Uranus and Neptune, and then inside the solar system, the terrestrial planets, Mercury, Venus, Mars, and Earth. So those are the planets. And then there are smaller bodies. Actually, these are elementary building blocks that are left over from the formation of the planets. To form a planet, you gather material, you make small dust particles that become little grains, little pebbles, and these pebbles stick together and form planets, big planets, EMOs, well, big objects that clump together and create a planet like Earth, for example. That's it. But in this process, there are some elementary building blocks that are forgotten, that get lost in the mix, and we end up in a planetary system with lots of small bodies, typically a few kilometers in size. The size of Paris for the biggest ones, the size of Romans for the smallest ones, let's say. And then the size of a village in Vendée for the very small ones, the really tiny ones, the tiniest ones. So these bodies that are left over from the formation of the planets, There are a certain number that are relatively close to the sun. Typically, for example, for what we call the asteroid belt, all these small bodies that are between Mars and Jupiter, these are bodies that are a few kilometers across, or, well, the largest ones are 500, 1,000 kilometers, but there are only a few of those. Most are just a few kilometers wide. These are asteroids. So these are objects that are close to the sun, and so there's no more ice, because if there were ice, well, it would have evaporated. We're close to the sun, so they're mostly rocky. And then, farther out, beyond Neptune there, we also have remnants from the formation of the solar system. And these are small bodies, but they're far enough away to contain volatiles. Ices of carbon monoxide, carbon dioxide, and especially water ice, because water forms quite naturally. And so these objects contain ices, and they're far away and they're quiet. And from time to time, well, they're disturbed by the passage of a star close to the sun or by the gravitational disturbances of the planets. And from time to time, they're put on orbits that make them approach periodically or almost periodically close to the sun. And when they get close to the sun, well, what has to happen happens. The ice evaporates, or rather sublimates exactly. And so they eject dust. All the small rocks on the surface are pushed into space, and that creates those gigantic comet tails. So, to answer your question, the difference between an asteroid and a comet is that an asteroid is more of a rocky object, which are on rather circular or almost circular orbits and are inactive with no evaporation or surface activity. Whereas comets are those objects that contain more volatiles, more ices far from the sun. To keep them for 4 to 4.5 billion years, because they formed at the same time as the Earth, 4 to 4.5 billion years ago, but they were frozen far away. And from time to time, they are brought close to the sun, so on very elliptical orbits, coming closer, moving away, coming closer, moving away. And then when they get close to the sun, there is cometary activity, which we call cometary activity, and it goes in all directions. So that's the difference between comets and asteroids. So in the Beta Pictoris system, we have both, because we observe a lot of dust. There's a dust disk. That's actually how it was detected the first time we saw the dust disk. And to produce this dust, well, one of the best ways is probably collisions between asteroids that crash from time to time. Poof, it creates a big cloud of dust that's spread throughout the system. So we think there are a lot of asteroid-like bodies. But there are also objects that evaporate, like comets, and there we can see the cloud of gas. When it passes in front of the star, and that's what made it possible to detect and study all these small bodies in very, very great detail. It's crazy when you think about it. These are bodies just a few kilometers across, located 60 light years away. And in the end, we're able to study the composition. The properties, well, we haven't actually seen them. We've just seen their shadow pass in front of the star. I think that here
it could be interesting because these are bodies that are quite far out in a solar system to begin with, and they still contain volatile materials. Can't we use them to go back in time a little and get information about the formation of the system? Solar system, about the elements that were present in that system.
So, actually, what you're describing here is our ability to reconstruct the physical conditions. The ones that led to the formation of a planetary system or solar systems, that's something that's widely used in the study of comets in the solar system, all right? When we study comets in the solar system today, we think it will give us clues about what happened 4.5 billion years ago when the sun was formed. And in particular, the distribution of elements, ices, and rocks depending on the distance from the star, as well as the distribution of isotopes. So when we talk about isotopes, we're talking about elements like hydrogen, oxygen, carbon, nitrogen, and so on. There are several forms of these elements depending on the number of neutrons in the nucleus. And so, for example, carbon, there's carbon-12, there's carbon-13, and there's carbon-14, which is used to date objects in archaeology. All right, so there are several kinds of isotopes of elements, and hydrogen, for example, has an isotope called deuterium. And so we can quantify the proportions of the different isotopes, in other words, the composition. And so for the solar system, that's what we do with comets. We try to determine, for example, how much deuterium there is, the fraction of deuterium in comet water. And to answer a difficult question, where does the water on Earth come from? It's a really difficult question, and we hope to provide some answers by measuring the isotopic composition of comets in the solar system. So, for exocomets, we're not there yet, actually. That's the truth. Right now, we're making the first measurements of the composition of these objects, and we're at the stage where we're trying to understand whether they formed far away, close by, or things like that. But it gives us clues about the mechanisms that might have taken place in another planetary system with a different planet configuration to see the diversity. Because one of the big lessons from the last 30 years of discovering exoplanetary systems, we know several thousand today, is diversity. Planetary systems are incredibly diverse, just absolutely amazing. Uh, In fact, 30 years ago, I still remember conferences where people discussed what kinds of planets we might discover back when we hadn't found any yet. And I assure you, everyone took the solar system as a model, thinking, well, we were going to look for giant planets that orbit over several decades, like Jupiter and Saturn, and then terrestrial planets that orbit over several years, like Venus, Mars, and Earth. All right, we were actually looking for solar systems. And what did we discover? We didn't discover solar systems. We discovered a bunch of things that don't look anything like the solar system. It's planets that we're discovering, and some of them are on very elliptical orbits. There are planets that are very, very massive, that are 10 times the mass of Jupiter. There are planets for which we have no equivalent in the solar system, with a mass between that of terrestrial planets and that of gas giants. There's a clear dichotomy in the solar system. We have the most massive terrestrial planets, with the two most massive being Earth and Venus, which have about the same mass, and then we have the gas giants. The least massive of these gas giants are Uranus and Neptune. That's 14 and 17 times the mass of Earth, so you see between 1 time the mass of Earth and 14 times the mass of Earth. There's nothing in the solar system, and this dichotomy allows us to easily classify. There you go. When it's less than 1 Earth mass, it's rocky. When it's more than 10 times the mass of the Earth, it's a giant gas planet. Now you find an object that's 7 times the mass of the Earth. What is it? Is it a gas giant or a terrestrial planet? Okay. We didn't know, so what we did is we discovered lots of systems that are very different from the solar system, with planets that have no equivalent in the solar system. We tried to understand them. So these planets have an intermediate mass between 5 and 10 times Earth's. In the end, the less massive ones, up to maybe 5, 6, 7 times the mass of the Earth, are probably rocky terrestrial planets. And then there's a range of intermediate planets which look more like what we call mini Neptunes, like Neptunes, but a bit smaller. But it's still a field we're currently exploring today. We have part of the answer. We understand the complexity, and in the end, the very simple model we had 30 years ago about the formation of the solar system was correct in its broad outlines, but in the details there were lots of things we didn't understand, and that we now understand thanks to the observation of systems very different from the solar system. All right.
So now we've detected several thousand of exoplanets. Have we still managed to find one that would resemble Earth or not at all?
One that would resemble Earth? Well, it depends on what we call resembling Earth. It's a difficult question, and many are trying to find an Earth-like planet. Actually, right? That's kind of the holy grail for a number of people who are searching for exoplanets, thinking if I find something that looks the most like Earth, I'll be happy actually, right? We really like our planet Earth, obviously. So we'd like to find something that resembles it. That's only natural actually, right? So to answer your question, no, we haven't found something that's 100% like Earth, but it all depends on the properties you're looking for. If you just want to find a planet that has the same mass as Earth, that's possible. Now we know a few planets that have masses similar to Earth's mass. If you want a planet that's about the same size as Earth, now we know a few planets that are about the same size as Earth. Now, if you want a planet like Earth, it's not just its size and mass, it's also about where it is in the solar system. It's at the right distance from the sun, it's at the right distance, not too close, so there can be water, liquid water, and not too far, so the water isn't frozen. So, what we call the habitable zone, the right distance from the star, which allows water to be in liquid form on the surface. If there's an atmosphere, that's it. Those are basically the general ideas. And so now, if you tell me about a planet in the habitable zone, we know of planets in habitable zones. But many of these planets are giant gaseous planets, so they don't look like Earth. And today we know a few. So we could say TRAPPIST-1e, for example, which is a planet that's a little smaller than Earth, which is roughly in the right zone. So it could resemble Earth, except that all these planets, you see, they also have different properties. It's that they don't orbit stars like the sun to discover small planets. We find them more easily around small stars. And TRAPPIST-1, for example, which is the star around which the planet TRAPPIST-1e orbits. It's a very, 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 very small star, very active, not very bright, not very hot. And actually, the planet is in the habitable zone because it's very close to a star that's not very hot, right? So this planet, in some of its properties, is similar to Earth, but in other properties, it's not like Earth. So if you tell me, I want a planet that looks like Earth, well, today we don't have one. Then, after that, we could even go further. I want a planet with an atmosphere of oxygen and nitrogen, for example. Well, that's something else entirely. So today we have planets that have good properties to resemble Earth, possibly good properties to allow for life. The emergence of complex chemical reactions that we could call life, but nothing that really resembles, well, that is the twin planet of Earth. We have more like cousins, let's put it that way. We have cousins of Earth, but we don't yet have a twin planet of Earth.
So Planet B isn't coming anytime soon?
Well, there are space missions that are looking for planets that are more similar. For example, like the European Space Agency's Plato mission, which is searching for planets, exactly in the way I described to you earlier. By looking for planets passing in front of the star, by measuring the brightness of several hundreds of thousands of stars. From time to time, we see one that's a little dimmer, but then we say, hey, there's a planet passing in front. So this Plato mission from the European Space Agency will be launched at the beginning of 2027. So soon and in a few years, we can hope to have planets that are about the size of Earth and that orbit stars like the sun. And with orbital periods close to a year, so maybe Plato will discover planets that, at least in those respects, will resemble Earth. So it's not for right now. But if we're not too demanding, what do we require for something to resemble Earth? In 4 or 5 years, you'll invite me again, and I'll describe to you the planets discovered by the Plato mission.
With pleasure. Sometimes we hear in certain newspapers and some shows about potential traces of life on exoplanets. Are these serious announcements? How do we study these kinds of things? And do we have any real results on these questions?
So we do have results, but let me stop you right there. There's really nothing. Well, I can't say serious because that would be too harsh, but nothing concrete. Nothing concrete. Yes, that's it. So there are some interesting things, that's undeniable, but often you have suggested, Often these are announcements that are a bit exaggerated, and the results can be interesting, and sometimes they can be hyped up a bit to create some buzz. Uh, and something that's just interesting ends up in the newspapers. It's happened to me before to hear we've discovered life, etc. And no, for now we haven't discovered any signs of life on these exoplanets, but we have discovered some interesting things. The latest announcement that was a bit overhyped was the discovery of dimethyl sulfide DMS, a somewhat complex molecule, basically two methyl radicals and a sulfur atom in the center, so a sulfur-based molecule, and it's this molecule. On Earth, it is produced by living organisms. Actually, it's a somewhat complex chemistry with sulfur. And on Earth, well, it's produced by living organisms. So there's a planet. We did it. We studied the spectrum when it passed in front of the star. Same thing, we broke down the light from the star when the planet passes in front. We saw the signatures of a few of a compound. And from exaggeration to exaggeration, it ended up in the newspapers. We discovered life on this planet. In fact, in practice, there are two pitfalls that I can tell you about. The first is, actually, we're not sure if it was really dimethyl sulfide that was detected, because the signal is, when I look at it. Later, I went to see the article. What? Well, yes, yeah, well, yes.
Ouais. Bon.
It could be, yeah. But it's not very, the detection is really far from convincing. It could be a lot of other things, you know, it could be that, but it could be a lot of other things. And even if that's what was observed, we're far from having proven that it was biological mechanisms producing this molecule. So there are really two exaggerations, both in the detection and in its interpretation, which means that in this case, it's actually pretty questionable, right? But let's stay positive after all. Beyond the exaggeration, it still shows that with the instruments we have today, among others, the James Webb Telescope and the Hubble Telescope. I hope we don't forget it because we still use it today for lots of observations, of course. The discoveries of exocomets that I was describing to you earlier, that was done with the Hubble telescope, not at all with the James Webb Space Telescope. We can't really study exocomets, or it's very difficult with the James Webb Space Telescope, so we use the Hubble telescope for that. But the James Webb Telescope for detecting these complex molecules is still a very powerful instrument. So I'm going to keep the positive message from this announcement about methyl sulfate, which might need to be reconsidered. It's that we're really at a time when we're able to characterize exoplanet atmospheres in a relatively detailed way and hope to detect things that could be indicators of complex chemistry. And so the beginnings of the discovery of life on these planets. So it's just the beginnings, you know, but still, it's interesting. Let's stay positive.
We discussed James Webb and Hubble. Are the astrophysicists who study exoplanets then? Do they work with laboratories? Do they work with agencies to agree on the tools that will be launched? Because I suppose there's actually a dialogue between the two, interactions between the two.
Yes, yes. So instruments like James Webb or future instruments, the Plato mission, as I was describing, or the instruments that in the coming decades will be launched, are defined by the scientific teams. In fact, at NASA or at ESA, the European Space Agency, there are people who design instruments, but they don't design them with an idea like, hey, we're going to make an instrument that does this and so on. There's really an interaction, and it's actually more the scientific teams that say, with the technologies we have today, we could make this kind of observation, this kind of measurement. And we know with the scientific knowledge we have today that these measurements will allow us to answer this kind of question. And actually, there are a lot of, well, yes, exchanges within the communities and at the international level. In fact, you know, the European teams, the American teams, who exchange with Japanese, Indian teams, and so on, who discuss what we can do with the instruments we can develop today, and who define the instruments that will be built in 10 or 20 years. Between the moment when there's a first idea, it's often, by the way, it's usually the scientific teams who at the beginning provide the initial impetus. By saying we know this type of object, we'll be able to characterize them better with this type of observation. So it's more about the impulse. It mostly comes from there, trying to do something that's realistic technically or economically. That is, ideally, it would be to have a 100-meter instrument in space, but economically, well, that's just not possible, you know? So the teams say to themselves, hey, it would be possible to do this kind of observation because we're going to understand something better. Actually, the scientist, his job is to identify the right questions, basically. It's not about finding the answers, finding the answer. Once you've found the right question, it's a technical matter. Finding the right question, that's really the researcher's job. That's what I always explain. The researcher's job isn't to find the answers, it's to find the questions. So the scientific teams define the scientific objectives and then go to the technical teams to say, look, it would be good to do this. And they lobby space agencies to design instruments that will help answer these questions. And it's a process that happens all the time. Because between the initial emergence of an idea like, hey, it would be good to build that kind of instrument, and the instrument that's actually in space making observations, at least 20 years go by. So it's really a very long process of discussion and design. And then there are debates, sometimes technical debates. That is to say, I'd really like to reach a certain resolution for my instrument. And then the technical side says, yes, but that's going to be complicated. Or often it's a balance between, for example, I'll give an example, sensitivity and resolution. So then the scientific teams, well, they debate. Some will prefer resolution, others will prefer sensitivity, obviously. And then, well, in the end, a compromise is found. And then the space agencies accept the instrument, and then it's launched, and then it's used like the James Webb. For the past few years in James Webb's case, or for decades in Hubble's case, which was launched back in 1991, and it's been in space for 35 years and is still providing results. I mean, it's really... Well, right now, when I leave these studios, I will get to work on it, finalizing an article based on observations we made last year, in September last year, 6 months ago, with the Hubble telescope. So you see, it's really an instrument, really very, very, very powerful. And it has changed our ability to study these exoplanets. Really, if there hadn't been the Hubble telescope,
We wouldn't have been able to find them.
no, not to find them. We made observations. Well, ground-based observations for radial velocities, space-based observations for transits, but the Hubble telescope is for studying them, okay? Actually, the Hubble telescope studies planets discovered by other instruments.
All right, I kind of feel like it's a lot more interactive than I originally imagined. And I think a lot of people imagine the world of science that way. And I feel like there's a lot of dialogue between different people, between different scientists, whether it's for analyzing results or designing instruments.
Yes, so actually science isn't... A researcher doesn't work alone in his tower saying, hey, I've got a good idea, I'll do my calculation, and that's it, it's done. Actually, to bring out ideas and to know if these ideas are interesting, that's a difficult question. What is really interesting to know deep down? Well, it's always through interaction with others. Others who say, yeah, if you understand this better, then I'll be able to understand something else better. So an idea is only interesting if it interacts with another idea, but an idea on its own, well, a calculation, the result of a calculation on its own. If it doesn't feed into another piece of knowledge, it's not really useful knowledge. And interesting, useful knowledge is knowledge that interacts with other knowledge. So to answer your question, yes, the world of research is a world that is constantly interacting. So we could have an idyllic view by saying it's people who collaborate, but that's not always the case. Sometimes there are people who are a bit in competition, who would like to make a discovery before someone else, or who think their topic is more interesting than their neighbors, and who puts pressure, for example, on a space agency to build their instrument rather than someone else's. So there is also competition, a kind of emulation, let's say, but yes. Donc, oui, by nature, it's a world that interacts a lot. It can't exist if it doesn't interact because knowledge only progresses collectively, you know. It's not about an individual, so it's necessarily, well, there are also sometimes interactions that aren't destructive but are a bit rougher, let's say. So that's it. Uh,
To go back a bit, about exoplanets, we've used various names, sometimes with letters and numbers, other times more poetic ones. So how do we choose the names of exoplanets then?
well, that's a very, very broad debate. The current nomenclature for exoplanets, to designate a planet, what we do is use the name of the star. So stars are catalogued, and there are several catalogs, you know, and we add a letter to the name of the star to indicate. For example, I mentioned Beta Pictoris b earlier, so it's a planet that orbits the star Beta Pictoris. And when we discover a planet around a star, we name it after the star with a small b, so why b? Does that mean A refers to the star? So it's a binary system, like I described at the very beginning. It's a binary system of two objects orbiting around each other. A is the star, and the first one we discover orbiting around it, we'll call it B. If we discover another planet, a second planet, we'll call it little c. And if we discover another planet, we'll call it little d, little e. Earlier, I was talking about TRAPPIST, TRAPPIST 1e. It's the fourth planet that orbits around the star TRAPPIST 1. Okay, all right. So that's the nomenclature. So sometimes it makes things that are oh, not too difficult. Beta Pictoris b, or the first planet around a sun-like star, 51 Peg b. It's planet B, the first one that was discovered around the star 51 Peg. And it's the 51st star in the constellation Pegasus. So the constellation Pegasus that everyone can see in the autumn sky, it forms the great square of Pegasus. Well, in this constellation, there was an 18th century astronomer who numbered all the stars from 1 to, well, those that are visible to the naked eye. So and there's the 51st one, there you go. And so the first planet that was discovered, we called it 51 Peg b. So that comes later when we find planets around stars that have slightly more complicated catalog names. Earlier, I mentioned HD 209,458 b well, because it's the Henry Dreyer catalog HD, and he cataloged several 100,000 stars, and this one is the 209,458th in that catalog, so it's called HD 209,458. Then we added a little b, right? So that's how the names work. And well, after that, there are people who work on microlensing. So it's another technique to discover exoplanets. So that creates really long names that I can't give you. I don't even remember them myself. So at first we settled for that, and anyway, we'll always keep that nomenclature. Even if we give the planets nicknames, we'll always keep this nomenclature because it's necessary for cataloging to make a catalog. You can't make a catalog of several tens of thousands of planets otherwise. To refer to them each time, we'd need to name each one and create a naming process. So basically, the nomenclature I just described to you is very, very practical. It works. So we're always going to keep it. I have no doubt about that. It's like your social security number, basically. You are given a name. There you go, Mr. Pauly. But we know very well that you can have a namesake. That for some, when you need to catalog 65 million people, it's more practical to have a number which is, I don't know the other digits, but there you go, a somewhat complicated name, but it's very practical. Well, we have the same thing for planets. But then there are still planets that we'd really like to give a name to. A name that's a bit easier than HD 209,458b. And it took a while for a lot of reasons, but it was complicated to define a process. To give names, and then people didn't agree. The first discoverers were reluctant to give names. When the discoverers are reluctant, it makes things complicated. And then who gives the name? How do we choose the name? It's complicated. And like planets, there is still an emotional side to it. Giving a name is a sensitive subject, actually, having taken part in the first campaigns that gave names. I can assure you that sometimes we're surprised by the reaction because, yes, we realize that it's a sensitive subject. Well, giving a name, yes, that's it. It makes something feel closer, so that's it. It was complicated, but in the end, we came to an agreement. Well, at some point, yes, it was in the early years, well, between 2010 and 2015. There were campaigns, especially coming from the United States, where some people started saying there's still no name for the planets. It had been 15 or 20 years since they were discovered and still no name, so some people wanted to give them names. There were campaigns that started to be organized by private groups, individuals, and even paid campaigns. There are always people who find a way to make a bit of money. And there were paid campaigns where someone would open a website and say, well, if you pay, you can vote for the name and so on. And the name you chose would be given to this planet by individuals, or rather groups of individuals who had no particular legitimacy to do so. And then we thought we had to do something. So the International Astronomical Union, at that time, I was president of the Exoplanet Commission of the International Astronomical Union. The International Astronomical Union is like the UN for astronomers. It brings together 12,000 professional astronomers from all over the world, from more than 140 different countries. So it's really, yeah. It's the organization that brings together all the astronomers who work on astronomical objects. And then we thought we have to do something, so we organized campaigns, this time under the auspices of the International Astronomical Union, with rules about the names we could give and those we couldn't give. And campaigns that were aimed at the general public. People could, this time for free, vote. There were national campaigns. There was a campaign in France that was organized. And so there are names that were given, and now we have about 200 planets that we've named, that we've given names to. It's a small number, actually, huh? But well, it's a start. It's a complicated process, having participated very, very closely, very actively in the first campaign. We had questions we hadn't thought of. If you want to name a planet after someone, what criteria do you set for that name to be acceptable or not acceptable? It's complicated. And so, well, there you go. So if you want to use God's names, and that's actually quite often what's chosen in the end, try to have coverage of different mythologies, different civilizations. So there you go. And so, for example, there are names that have been given. In Japan, they had a lot of activity. And so quite a few names that were given are from gods of Japanese mythology, things like that. There are even names from Thai mythology for some planets, because in Thailand there is also a movement. And there are names from mythology, well, names that were given by astronomers from Morocco as well. So you see a great diversity of names. I don't have the examples in front of me, so you can look up the different names that have been given. But there you go, there are plenty of names that have been given. It's a short process, but it's complicated. Then you also have to choose which planets you're going to name. Since we've identified so many of them, which ones are we going to name? And there too, we had to define some criteria. And it happens little by little because, as I told you at the beginning, at first, it's a sensitive subject. And you can make mistakes which lead to misunderstandings. especially if you name them after people. So you have to, well, if, well, it's complicated. So it's a long process and it's ongoing and it will continue. But, well, today we have more than 5,000 known exoplanets. We're not going to name them all, and that's okay. It's okay.
So we're coming to the end of our interview. There's a question I really like to ask. Do you have any reading recommendations for those who'd like to learn a little more? So regarding the study of exoplanets, are there any books, whether by you or by others? Others from your colleagues that you would recommend then?
That's a great question because, as it happens, my colleague Guillaume Ebrard has just published a book on exoplanets, extraordinary planets. I don't remember the exact title. I'm sorry. I hope Guillaume will forgive me. I think it's Extraordinary Worlds or Extraordinary Planets.
We'll put it in the description.
And it was just published with amazing illustrations. And it's full of short chapters about all the topics we've discussed today. Totally accessible for a general audience. And yes, I can really recommend it. People will no doubt enjoy reading it a lot.
All right. One last question to finish. Are we expecting to make some discoveries in the coming years? Yes.
So yes, it's not even that we expect it. I'm sure we will make some. There's absolutely no doubt.
And do we already have predictions, things we would expect to see? Well, no.
Exactly. So my first answer is yes, we're going to discover a lot of things. And no, I don't know what it is. And I don't know what it is because precisely we're going to discover it. If I could tell you, yes, we're going to discover this, it would mean we already knew it deep down. Donc, I'm sure we're going to discover things, and that we're going to discover things we didn't plan to discover. That's what discovery is deep down. And well, over these last 30 years of exoplanet discoveries, it's amazing how many surprises we've had. Every time, basically, we have a prediction, we should see this, we should see that, we go and observe, and we find something else. And I even have a little joke, it's to poke fun at my theorist colleagues. When a theorist tells you there's no point in observing that it doesn't exist, or you won't be able to see it while it doesn't exist, the first thing an observer should do is go check to see if the theorist was wrong and that it does exist. So if an observer tells you, if a theorist tells you not to observe something, do it. That's a joke, of course. Theory is used to understand what we observe. And if we didn't have theorists who build our understanding of the world, what we observe wouldn't make any sense. You shouldn't just observe the existence of an object or the measurement of a quantity. You have to give it meaning. And for that theory, the fact that people understand things is very, very important. But we're going to make lots of discoveries, and I don't know what else.
Okay, well, I'll make the appointment then. We'll schedule another meeting to discuss these new discoveries.
Thank you. Thank you very much.
Thank you very much.